So our exam Wednesday will cover 7.4 and 7.5, which is about trigonometric equation solving. We'll also cover 8.1, 8.2, and 8.3. 8.1 was our introduction to polar coordinates. 8.2 is doing some polar graphing. And 8.3 is the polar form of complex numbers, which we're going to finish up today. Okay. I'll get a review posted for the exam later this afternoon, so you have that. I will also be around all day tomorrow. I have class at 11, but other than that, I'll be around my office all day tomorrow. We've got questions to go over things. Friday, we'll talk about final exam stuff, and then our final exam is scheduled for next Monday at 10 o'clock in here. So, almost done. Yes?
How long are the exams supposed to be?
The final?
Yeah, the final.
The final exam, it's scheduled for an hour and 50 minutes. I usually write it to take like an hour and 20-ish so that you have plenty of time to get it done. All right. Well, let's go on then and talk about our complex numbers. So talked a little bit last time about how we can graph complex numbers in the complex plane and associate a complex number with a point in the plane, thinking a bit about it in Cartesian or rectangular coordinates, if you will. But we've already talked about converting points in the plane to polar. So it's the exact same idea here. If I have this point, I'll call it A comma B, which corresponds to your A plus BI. Then this distance is the same as your R value, correct? That we did back in when we talked about converting to polar. Well, in this case, we refer to that, if I refer to my complex number as Z, that R is your modulus of the Z, or the square root of A squared plus B squared, just like it is before. This angle here is the same angle for polar that we would have before. So you can figure out your theta by doing tangent of theta is y over x, just like we talked about before, right? So when we do this, when we write this in polar form of your A plus BI, then my point here is my R, or my A comma B. We'll convert it over to polar, but notice that your A would be your R times your cosine of theta, from using that other conversion that we have, right? And your B would be your R times your sine of theta. So the way that we can write sorry about that. The way we can write, why are you doing that? The way we can write that is, you can put the modulus of Z out in front, or the R out in front, times cosine of theta plus I times sine of theta. So notice when I distribute the modulus of Z through, this is R cosine of theta. That's going to match up with your A. When I distribute this through over here, this is going to be R sine of theta. That's going to match up with your B. So when you convert this to polar form, this is the polar form of A plus BI, according to our picture. All right, so let's see if we can do these. I want to write, the first one asks us to write 5 root 3 plus 5i in polar form. Just like we did back in polar, the first thing I got to figure out was what the R value is. In this case, the R value is the modulus of the number. Remember, we calculate that as square root of the real part squared plus the imaginary part squared. 5 squared is 25. Square root of 3 squared is just 3. So this gives you 75 when you multiply that out. So you get 75 plus 25 under the radical. 75 plus 25 is 10. 75 plus 25 is 100. Square root of that gives you 10. That is absolutely nothing different than what we did when we converted to polar, right? The other part we use the tangent of theta equals y over x. Remember when we plot a polar point, try that again. When we plot a complex number, the imaginary part is the y, the real part is the x. So I'm doing y over x. 5's cancel, we get 1 over root 3. So what angle gives you a tangent equal to 1 over square root of 3? Pi over 6. I have to be a little bit careful. Remember, I need to make sure I'm in the correct quadrant. If this is my x and this is my y coordinate, both of them are positive. So which quadrant are we in? First, and pi over 6 is in quadrant 1, so we're good. So when we write this number in polar form, then, we will write it as 10 times cosine of pi over 6 plus I sine of pi over 6. And that is that same number in what we refer to as polar form. So if we do the next one, same idea. First step, calculate your modulus. Just like you do in polar, if this is my x and this is my y, I do square root of x squared plus y squared. That's going to give me 128. If you break it up, that'll give you 8 square root of 2. To figure out our theta again, we'll do tangent of theta is y over x. Again, imaginary part is the y, real part is the x. So 8 over negative 8 gives me negative 1. Also pay attention to what quadrant should we be in. If we were to plot this if we were to plot this complex number, what quadrant would you be in? This is negative and that's positive. What quadrant would you be in? The second quadrant, right? So you're looking for an angle, the angle, I should say, in quadrant 2 that gives you a tangent value equal to negative 1. What angle do you want? 3 pi over 4. Good. So this tells me that our theta is 3 pi over 4. So how would we write our complex number in polar form here? Yep, good. Exactly right. Notice this is exactly like what we did back in section 8.1, isn't it? It's not anything new. We're just writing it as a complex number rather than just having an x comma y and an r comma theta. Now we're just using the graphical representation of complex numbers and writing the complex number in this form. Is that okay? The last one you would do the same way. Notice that when you try to figure out your tangent value, you're going to get tangent of theta equals a half. So you'll do negative 3 over negative 6. So you'll have to use your calculator to approximate the theta. And make sure you're in which quadrant, by the way. This is negative and this is negative. What quadrant are you looking in? 3, right? So remember, when you do your inverse tangent on your calculator, you'll get an angle in quadrant 1. Since it's positive, you'll have to add pi to it to put in quadrant 3. So I'll leave that one for you for practice. But again, it's just like what we were doing back when we converted numbers to polar, or excuse me, converted points to polar. Why do I keep saying the wrong words today? My apologies. Any question on the process? Again, can't emphasize enough. Exact same process we did back in section 8.1. Nothing is different. We're just writing the answer as a complex number rather than as a point. Otherwise, it's the same problem you've already done before. Why do we care about complex numbers in polar form? I would be surprised if you weren't asking yourself that question. Right? This seems like, why would I do this? Right? What's the point? Why do I care? Well, this is why we care. You can remember how you multiply or divide complex numbers. Pardon me. When you multiply or divide complex numbers, in particular when you divide, you have to multiply by the complex conjugate and do some simplifying things. If we're in polar form, things get a little bit easier. So right now I'm just writing them side by side. Notice here everything is multiplied together. I can multiply in whatever order I want. So I can multiply my R1 and my R2 together, for example, and put that out in front instead. So I can make this R1 R2 times cosine of theta 1 plus I sine of theta 1 cosine of theta 2 plus I sine of theta 2. Nothing special there, right? That's just, I can multiply in whatever order I want. So I just rearranged it. So notice, before we do the next part, notice that part of multiplying your complex numbers together is multiplying the moduli together. Multiplying your R1 and your R2 together. That's kind of fun. Okay. Let's look at this part. If we multiply that out, you'll have cosine of theta 1, cosine of theta 2. When I multiply the first pieces together, right? When you multiply this and this together. Now, I know I have to do, and if I'm thinking about FOIL, I have to do an outer and an inner. But let's multiply this and this together. What do you get when you multiply those two things together? Not a trick question. What do you get when you multiply those two together? Then you get I squared, and then you'll get what else? Sine squared. No, it's not quite sine squared because there's different things on the inside, right? So it's just sine of theta 1 times sine of theta 2, right? What's I squared the same thing as? -1, right? So I can actually write this as minus sine theta 1 sine theta 2. Now, let's do the other pieces. Notice that when you multiply this one and this one, you'll have an I in it. And when you multiply this one and this one, you'll have an I in it, right? So I can factor the I out. When I multiply these two together, we get sine of theta 1 cosine of theta 2. What do you get when you multiply these two together? Yeah, we'll get sine of theta 2 cosine of theta 1. Now we're almost done. Let's look at the first part here. This should remind you of an identity. Part of the reason why we're doing this last is it reminds us of things from what we did before, since the final's coming up. What identity does this one remind you of? So what's it equal to? If it were equal to 1, I'd have to have the same argument, but it's the idea there. You think about something to substitute in there. What if I called this alpha and this beta, rather than a theta 1 and a theta 2? What does that remind you of? It was on the last exam. Guess we got some reviewing to do for the final. That's our sum formula for cosine, isn't it? Remember, when you do the sum formula for cosine, it's cosine, cosine minus sine, sine. Isn't that exactly what we have there? Okay. How about the second piece then? What's this one? It's the sum formula for sine. So notice, if you have your complex numbers in polar form, I can multiply them together by multiplying the moduli, and we call the thetas the argument for complex numbers. Multiply the moduli, add the arguments. That's a lot easier than what you typically go through for multiplying complex numbers together. Rather than going through the derivation, do you think you can figure out what you would do for dividing? When we multiplied the moduli. What do you think we would do when we divide? Instead of having R1 times R2, what do you think you would have? Yeah, R1 divided by R2. That's what goes out in front. When we multiplied, we added the angles. What do you think we're going to do when we divide instead of add? Subtract, yeah. So again, when your number or complex numbers are in polar form, adding and subtracting becomes a lot easier. These are your two formulas that you have. So again, when you multiply, you add the angles. When you divide, you subtract the angles. That's all we have to do. So let's look at the next couple of examples that we have here. They give you Z1 and they give you Z2 and ask you to find the product of them. So again, what do we do with the 5 and what do we do with the 3? Multiply them. Good. So 5 times 3 will give you 15. We have 5 pi over 6 for the angle for the first one. Pi over 3 for the second one. What do you do with those angles when you multiply? You add them, right? Pi over 3 is the same thing as 2 pi over 6 if I get a common denominator. So I would have cosine of 7 pi over 6 plus I sine of 7 pi over 6. And if the problem asks you to rewrite the complex number back in standard form, a plus bi, I can simplify this. What is cosine of 7 pi over 6 equal to? Cosine of 7 pi over 6 is equal to? Say again? It's the other one. Is it root 3 over 2? Yeah, then it'd be a negative because it's over in quadrant 3. And sine of pi over 7 pi over 6 is negative a half. So if I wanted to write it in standard form, I could write it that way. I could write it as negative 15 root 3 over 2 minus 15 halves I. Again, notice that the operation itself is easier, assuming you remember what the sine and cosine values are. If we divided rather than multiplied, what would we have? What do you do with the 5 over 3 when you divide? Or the 5 and the 3 when you divide? What do you get? What do you do with the 5? And what do you do with the 3? Divide them, good. And then what do you do with the angles? Rather than add them, you subtract them, good. We just said a second ago that pi over 3 is the same thing as 2 pi over 6. When we subtract 5 pi over 6 and 2 pi over 6, we get 3 pi over 6, which is the same thing as pi over 2. So we'll get cosine of pi over 2 plus I sine of pi over 2. What's cosine of pi over 2 equal to? 0, good. And sine of pi over 2 is 1. So we just end up with 5/3 I. Again, the idea here is it makes that's a lot easier to divide those two things together, or divide those two things by each other, I should say, when it's written in this form, isn't it? But it only took a couple of steps and we were done. All right, so what about the next one? If we wanted to do the product, I've got it written in degrees, but it doesn't really matter. It's the same principle. When you multiply, what do you do with the square root of 10 and the square root of 2? Multiply them. Square root of 10 times square root of 2 gives you square root of 20, which you can rewrite as 2 square root of 5. What do we do with the 240 and the 30? Add them. So we'll get cosine of 270 and sine of 270. Oops. If we think about quadrants, where is 270? That's there, isn't it? So what's cosine of 270? Zero. And sine of 270 is -1, since we're down here. So we get negative 2I root 5 when we're done. That's a 5. It's an ugly looking 5. How about now when we divide? What do you do with the square root of 10 and the square root of 2 when you divide? Divide them. Square root of 10 divided by square root of 2 will give you square root of 5. Because you just get the 10 over the 2 under the radical. When we divide, what do we do with the angles? Subtract. So we'll get cosine of 210 plus I sine of 210. Oops. 210 is the same thing as 7 pi over 6, right? Because 180 is here and then another 30 degrees. So we already did cosine and sine of 7 pi over 6 a minute ago. And so we'll get negative root 15 over 2 minus root 5 over 2i when we're done, when we distribute. All right, what questions do you have over these? Again, the idea here is once you have it in polar form, the computation should be straightforward. Should be relatively easy, right? Multiply your moduli, add your angles when you multiply, divide your multiply, subtract your angles when you divide. All right. Another thing that having your point in polar form having your complex number in polar form allows you to do is calculate powers quickly. Calculating a power is just a repeated multiplication, right? So if I'm going to multiply something over and over and over and over again, I'm just going to add the angle to itself over and over and over again, right? So if I start with r times cosine theta plus I sine theta, when I do that number to the nth power, I raise my modulus to the nth power. I multiply the r value by itself n times. But the angles we add. That's a lot faster than actually trying to multiply out that cosine theta plus I sine theta to itself that many times, right? I just have to add the angle to itself. This is what's called de Moivre's theorem. That's about as good as my French pronunciation gets, by the way. All right. So to be able to apply de Moivre's theorem, I have to put my complex number into polar form first, and then apply the n in the right spots. Okay. So again, I'm going to convert just this part to polar. So again, I need the r value or the modulus value, whichever way you want to think about it. We do square root of 1/2 squared plus negative root 3 over 2 squared. Because again, my 1/2 is playing the role of x. My negative root 3 over 2 is playing the role of y. Square 1/2, you get 1/4. Square root 3 over 2, you get 3/4. Add that together, you get 1. So we just end up with 1. to figure out the theta value. Again, the I part, the imaginary part, plays the role of y. The real part plays the role of x. So negative root 3 over 2 over 1/2 is tangent of theta. Simplify, we get negative root 3. Right? Well, if I'm just looking at root 3, what angle has a tangent equal to square root of 3? Pi over 3. What quadrant is this point in? If you think about it that way. What quadrant is 1/2 minus root 3 over 2I in? 4. So instead of using positive pi over 3, we would use negative. Yeah, just make it negative pi over 3. That works. Or you could use 5 pi over 3. But making it negative is just easier, isn't it? All right, so now I want to put this into polar form. What's the R? What's the modulus? 1. So I didn't really need to write it, but I will. 1. The angle is negative pi over 3. I need to leave myself a little bit more room, apparently. According to de Moivre's theorem, we will do 1 to the 15th power. That's simple. And we will multiply the angle by 15. So again, de Moivre's theorem says take the exponent, raise the r value to that same exponent. So that is 1 to the 15th. And like I said, where are we going to get when we do that? 1. Take your 15 and multiply it by each of your arguments. So we get 15 pi over 3 for each of them, negative 15 pi over 3. Well, the 15 pi over 3 simplifies down to negative 3 to 3 pi. So we get negative 3 pi for each of them. Negative 3 pi. Start rotating downward. There's negative 2 pi. Go around again, you end up here, don't we? What's cosine of negative 3 pi going to equal then? If we land here, what's your cosine of negative 3 pi going to equal? Negative 1. Sine of 3 pi is going to equal 0. Good. And so we just get negative 1 more done. Would you have guessed that we would have got negative 1 from this computation to start with? No. Okay. Much faster, right? Rather than trying to multiply that by itself 15 times. That's hard. That's a computer, but for you it's hard, right? If I'm trying to do it by hand, that's hard. It's not something you would want to do. What's that? Oh, it is negative 5 pi. You're right. Sorry. Good news is it doesn't change the answer. I'm still in the same spot. You're right. My bad. Thank you. Negative 5 pi just means that I rotate it around one more time. Still in the same spot. Thank you. All right, what about the next one? What do we compute first? What do you do first? Yeah, find the R. How do we find the R? Okay. Good. Root 3 squared is 3. 1 squared is 1. So you get square root of 4, which gives you 2. What else do we need to find? Theta. So what will our tangent of theta be equal to in this case? 1 over root 3. Good. Remember, it's y over x, correct? What angle has a tangent equal to 1 over root 3? Good. And is that in the correct quadrant for what we're looking for? Yep, it is, because we have root 3 plus I, correct? So what complex number in polar form are we now raising to the 5th power? How will we write what's supposed to be on the inside of those parentheses now? You're right. I want the complex form, the complex number in polar form first. But you're exactly right. What we need to do. What's the complex number in polar form going to be on the inside here? 2 times cosine 5 over 6 plus 5 sine 5 over 6. Good. That was converting the complex number to polar form. And now what do we do with the 5th power? Say it again. Yeah, so the 5 will get multiplied by the pi over 6. What about with the 2? Good. So it'll be 2 to the 5th cosine of 5 pi over 6 plus I sine of 5 pi over 6. Two to the 5th is 32. Cosine of 5 pi over 6 is negative root 3 over 2. Sine of pi over 6 is positive 1/2. If you distribute the 32 through, you'll get negative 16 root 3 plus 16i. That one okay? Does the process make sense, what we're doing? Again, notice the crux of this is converting a point to polar form, right? It's a good review for what we did back before break. That's okay? All right, I'll leave the other one there for practice for you. Let's talk about the last little bit here, which is finding roots of complex numbers. So we're going to work in reverse. Notice that when we took a number, a complex number in polar form, and raised it to the nth power, we multiplied the angle by the power, didn't we? Now, hopefully it's obvious. Taking a power and taking a root are the inverses of each other. So if I want to take the root of a complex number, rather than multiplying by the power, I want to really divide by it, right? Now it turns out, when we do that, we have several different roots that we can get. So if I want the nth root of z, or z to the 1 over n power, I'll do the nth root, the nth root of the r, and we will divide the angle by the n. But notice I'm leaving some space in here. We do the nth root of the modulus and divide by n. Because we're doing nth root, so we'll divide rather than multiply. But we also know that, pardon me, we also know that when if we do coterminal angles, we will get the same values out when we do the nth power. Well, I'm saying that wrong. If I do coterminal angles, I know that my sine and my cosine will give me the same values. So if I do multiples of 2 pi on top, I should get the same thing. It will give me distinct answers when I do my k going from 0, 1, 2, up to n minus 1. When I get up to the n for my k, I start repeating. Right. So let's see how this works, rather than me trying to explain more and more. Let's just see how this works, because the process is going to be the same for every single one of these problems. Your first step, just like every other step, is rewrite your complex number in polar form. When I have negative 32, that would be over here, wouldn't it? Notice that your distance from the origin is 32, and your angle is pi, isn't it? We agree with that? Okay. So that's where we get the 32 times cosine of pi plus I sine of pi. It says we want the fifth roots. The fifth roots. So again, we'll do the fifth root of 32. We'll divide the argument by 5. But then we got to do this coterminal angle idea. And we'll plug in the different values for k. What possible values are we going to plug in for k in this case? Since our n is 5, looking up above what I wrote, what values are you going to plug in for k in this case? 0 up to 4, right? Okay. So if you have k equals 0, we'll have 32 to the 1/5 power is just 2. Cosine of pi over 5 plus I sine of pi over 5. If k equals 1, we'll get cosine of 3 pi over 5 plus I sine of 3 pi over 5. K equals 2. We'll get 5 pi over 5, which is just pi. The next one will be 7 pi over 5 And the last one will be 9 pi over 5. Now let's just talk about this for just a second. Notice that a fifth root of a number, there's 5 complex fifth roots. When you did fifth roots before, back in algebra class before this, whenever you'd say the fifth root negative 32, you probably just said negative 2 and then we're done with it, right? But there are 4 other fifth roots of negative 32. They just all happen to be complex. Notice this one right here. The 2 cosine of pi plus I sine of pi, that gives you negative 2. That is the real one. But there's also 4 complex ones in here. Think about it from an angle standpoint. Let's draw it on the board real quick, and then we'll do another one real fast. Negative 32 was here, right? I want to raise something to get to the 5th power to get here. I better have an angle over here, pi over 5, so that when I do it 5 times, I land right here. But notice that if I use 2 pi over 5, which is about right here, if I do that 5 times, I also land right here. I land in the same spot. Because if I do this 5 times, 2 pi over 5 times 5 gives me 2 pi, not 2 pi over 5, 3 pi over 5, which is over here. I lied. It's over here. 3 pi over 5 times itself 5 times. Remember, you add the angle. 3 pi over 5, 5 times gives me the 3 pi, which is the same spot. 5 pi over 5 gives me the same spot and all the way down. Let's do one more, and then I'll post a couple more on Moodle so you can also see what the answers look like. Again, first step is to put it into polar form. 27i is right here. Because we would go straight up, correct? That makes your angle pi over 2. So if I want the cube roots, I'll divide the angle by 3. Well, I do the cube root of the modulus, but that's just like what you do for any real number, right? Just do the cube root of it, whatever root it is. Divide your modulus by 3. So dividing pi over 2 by 3 gives me pi over 6. And then do this coterminal business. All right, we're doing cube roots. So what values are you going to plug in for k if you're doing cube roots? 1 and 2. And 0, right? We want to do 0, 1, and 2. So if k is 0, we get 27 to the 1/3 is 3. We get cosine of pi over 6 plus I sine of pi over 6. If your k is 1, you get 2 pi plus pi gives me 3 pi over 6 is another pi over 2. And if you plug in 2, you get 3 cosine of 5 pi over 6 plus I sine of 5 pi over 6. Did I do that right? And those give you the cube roots that you want. All right. Like I said, I'll get a few of these, more of these. I'll do the last one there for certain. I'll do a few more of these for you on Moodle. I'll get a review sheet posted for your exam. So again, your exam is over 7.4 and 7.5, which is equation solving. 8.1 is polar, which you've certainly reviewed today, haven't we? Converting things to polar. 8.2 is doing polar graphs, and then 8.3 is the stuff with doing the complex numbers stuff. All right. Have a good one. We'll see you on Wednesday. And like I said, I'll be around all day tomorrow. I have class at 11, but other than that, I'll be around all day if you've got questions. I'm happy to answer. I'll be around this afternoon too, but tomorrow I'm definitely free all day, except for 11 to 12:15.